right. We've all been waiting. Today, we're going to ask the question, what does this have to do with this? Strap in. We're about to get into it. All right, so what am I talking about here? Okay. This is a motherboard from a build I did a long time ago. I didn't actually complete it. I'm not quite sure why. I do a lot of PC builds, mods, things like that. That's how I kind of got into cars. And for a long time now, I've been the kind of the person who does this sort of thing. If you are not PC inclined, get out of there. What is this? Okay. So that's a CPU. It's a standard Intel Core. It's a couple generations old, but it's, I think, almost certainly a quad core. It's unusual from other CPUs because, as you can see, it's got a very shiny, almost reflective copper surface. And that is because I lapped it like running laps. Used a combination of different grits of sandpaper, took the nickel jacket right off it, and got down to the exposed copper core, which then we maximize for contact with a heatsink. Why would we go to all that trouble? Let's go to the whiteboard. All right. Sorry for the aspect ratio change, but this is the best for this format. Anyway, so what we were looking at just now is the practice of overclocking, which is taking a CPU, which operates at a standard clock cycle, let's say something like 3.2 gigahertz, which is a way of saying the motherboard of a computer, which is the main board that everything connects into, operates on a standard sort of cycle. And so every time one of these occurs, an instruction set is processed. Okay. The CPU attaches to the motherboard, central processing unit. It's the main chip. And that will tend to have something like a multiplier. I promise this will all become relevant if you're just like, get to the car stuff. So this will look something like this. Actually, that's pretty terrible. And I'm going to do this as sine waves because it's easier. This would have much more frequency. Right? And so again, on each and every one of these, a clock cycle, an instruction is processed. Okay? And this core speed is how we describe how fast that chip is. Okay? So, excuse me, it's winter here, so like the weather, my God. What if I want a faster chip? Well, I can literally go out and buy a whole other chip, 3.8 gigahertz, right? Or, wouldn't it be nice if I could turn a 3.2 gigahertz chip into a 3.8 gigahertz chip? How does one do that? Well, two things. The chip runs at a standard voltage, which I'll put here. It starts here, okay? And when it's powered on, it'll come up to here, and it'll hold that power. And that is, if we'll say it's something like, honestly, it's not that high. Like 1.34 volts DC. It's not a lot, right? And at that voltage, it can execute this clock cycle all day long. And the BIOS, which is a lot like an ECU, tells the chip what voltage to run at and what clock cycle to run at. And so if we want to increase our chip from 3.2 to to 3.8, and we also want to increase our voltage to something like 1.47, right? Now I'm operating that much higher. And again, I modify the BIOS to up all that stuff. I can get the chip to operate at 3.8 gigahertz. Wow. So like free energy, right? Not quite. The other thing we have to monitor is temperature, and we have to think about load. So as the load of the chip increases, so does the temperature to a sort of maximum point. And this would be 100% max load. Right at this point right here. That's 100%. Which, hint, hint, is very similar to a WOT condition. Okay? And this right here would be my Tmax. Okay? That was all before. Now I increase the voltage, and I tell it to run at a higher clock cycle. Guess what happens? Bam! Right? Sad chip. Because that heat, if it exceeds the maximum temp the chip can run at, guess what? It melts the chip, right? So, managing our thermal max becomes the name of the game. And that's why on a system like the one I showed you, I would lap the CPU to increase the contact between the chip and the cooler, right? And I would put a massive cooling unit on that chip. And if I did increase my power and managed my temperatures intelligently, then I can get away with this. But I have to be the one to engineer the system to take the increased thermal load. So let's take another look at how to apply this. All right, so we're going to talk about power enrichment, which is counterintuitive because really the question is, how lean can you go? Let me explain. So, remember we have an imaginary cylinder and it has a piston in it. And that piston is traveling downwards. And it's compressing a mixture of fuel and oxygen molecules. Okay. And as it pushes down, my temperatures are going up. Okay. But I also have down here, of course, my friend the spark plug. And at the critical moment, that sparks, and we suddenly go violently upwards, right? That's how we do this. And we know that if we want to describe the composition of that gaseous state, we talk about lambda, otherwise known as the AFR, which we know for 93 octane fuel with 10% ethanol, every time, we know that that AFR equals 14.1 oxygen molecules to 1 of gas, which is okay. And we also know that that is a stoichiometric burn, which corresponds with 1 lambda. Okay. So, we know that in an idle state, we want to have this stoichiometric mixture. Why? Because stoichiometric perfectly burns. There's no gas left over, there's no oxygen left over, there's no residues, and it gives the most power. And so the greedy among you should immediately have thought, well, now wait a minute. If stoichiometric, or a ratio of 14.10, gives me the most power possible out of a combustion cycle, why would I only use it at idle? I should be using it at wide open throttle. And let's think about that. So, if I drew a graph, and I'm again measuring temperatures, and I'm measuring engine load, I will find in the world of idle that the car comes up to about that temp. Easily managed. As I begin adding power, temperature starts going up pretty linearly. Okay. And at some point, you would find it's cute at first, and then eventually it'll tend towards asymptotic, but we're not going to worry about that too much. Because here's the thing, we would never get there. This is where your safe operating zone would be. Above this threshold here, though, your temps would go astronomically insane. They would be where you would explode. And it is, in fact, where you start to see detonation. And when things get really bad, you actually get pre-ignition. And let's explain what the difference is. Detonation is when a combustion event occurs, right? We had a burst from our spark. And then as the piston is going back up, there's a little bit of gas left. And the cylinder is so hot from the loading we've been doing that the remaining gas, instead of hitting the exhaust and going out as a rich mixture, which it should, and if it hits a hot exhaust, it goes pop, 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 right? Everybody loves the popcorn tune. But this detonation, it actually occurs within the cylinder itself. And that leads to the very sour monster of knock and knock retard. Knock retard is something we look for in our logs because the second we see it, we know we've reached for too much power. We've run too hot. We'll get to that in a sec. Pre-ignition is the absolute doomsday scenario where the cylinder is compressing an unignited mixture, and before the spark plug even goes off, the temperature's so high that the gas spontaneously combusts. And that's where you have the piston going down, the gas going up. That is how you grenade an engine. Okay? Shredded. Blown block, right? Punch the metal right through the block. Amazing. So, how do we manage this? Well, we have another graph here. We manage our temps. All right, so imagine we have a variety of lambdas here. We have one which is 1.0, and as I slide along this axis, I make my lambda richer down to something like 0.8. God, sorry. My father had this too, like, smart guys, but handwriting's terrible. All right, 0.80. Okay, so we perfectly stoic, very rich. Okay, because the cool thing about this is if we were to map all our watt temperatures, okay, watt at a 1.0 would be astronomically high. Watt at 0.8 would be quite low. The temp, okay? That would be quite low. That would be quite hot, right? And I could get exact numbers. Your homework is to find these exact numbers. Yeah, should I show you? This is something like 2200 Fahrenheit or something. I mean, ridiculous, right? Like iron melting temperatures, okay? And then we know, let's say it's here, there's a critical threshold. And we know that above that critical threshold is when we see knock and detonation. And we know that this is inefficient. And this is our cool zone, right? Where, and I never actually drew the temps here. So this function would look something like this, right? Temps going down, the richer we make the mixture. And why is this? Because we're adding extra gas that floods the cylinder. Some of that gas doesn't get burned off, and that deliciously cooling mist, just like mist on a warm summer's day, if someone mists you with one of those little fans, right? It feels great, right? It cools things down, right? And it helps also preserve. Remember, there's like a sheen of oil on these walls here. There's also a fun little puddle of fuel that can form on the piston, but that we're not going to get into all that. Bottom line is, we are deliberately managing the engine to inhabit this zone between inefficient and the critical threshold, okay? And it turns out that can be from anywhere from like 0.82 up to something quite crazy like 0.88. We want to live in this world, and what we're trying to set is our power enrichment lambda. Okay? And what I can do, if the car comes to me in a state where it's commanding 0.82 as its power enriched lambda, I could set it to 0.85. That will lean it out, it will make more power, and it will produce more heat. And as long as I can manage that heat, then I'll be good to go. And that's the name of the game. Let's go see in the software how we do all this. All right, let's take a look at some of what we were talking about just then with the whiteboard. I have a tune here, or a log rather. This is a log from early on in my tuning process, back when I was still touching math a good bit. And you can see here we were logging all kinds of things. And I was interested in this log because it has a couple of watt poles. And if I actually zoom in on that a little bit, okay. Here you can see Watt Mountain. Looks like we got to 5,700. Something might have happened there. But when you look at this, you can see a couple of things. Let's see here. First of all, engine coolant temp is at 189 Fahrenheit. Cylinder head temp at 199. Those are quite cool. And my fuel WB down here, WB EQ ratio bank is telling me I'm a 0.99, 1.0. Stoic, right? Cool, clean. It's what I would expect here when I'm only at 1900 RPM. I come here to the bottom of the mountain. Something's happened, right? The RPMs are going up. The wide bands have richened up a little bit. And as I look at my temps here, 189, 199, okay? As I proceed here, these temps in the moment, looks like cylinder head went up, coolant temp is staying roughly 189. You can see here we've richened up to 0.83 on the wideband. it's telling us I'm commanding 0.82 and 0.879 across the banks, and then there's also the averaged. These are a little more theoretical. They're informative, but like don't trust them for actuals. The wide bands are your friends, right? They tell you the actuals, okay? And once again, bless the fine people at Ford for giving you a car that already has 2 wideband sensors installed. Chevrolet doesn't do that. Just saying. And if we come here to the top of the mountain, peak power is 5,700. We see we were richening to 0.83. A little bit there, 0.83, 0.83. Okay. And now let's look at these temps here. Coolant 189, 200. Now, that was the acceleration event. Watch, if we move this a little. As we go out past the acceleration event, you'll see here that cylinder head temp has climbed and engine coolant temp has climbed. We've also leaned out here, right, because I've let off the pedal. So now we are not commanding fuel at all. It's the cylinder, or the crankshaft just rolling, right, so it produces a vacuum state, sucking in all kinds of air. No fuel's being delivered because we let off the pedal. So that's why we see a nice big lambda like that. But our temps have gone up. Let's see, max 203. Do we go any higher? Nope. And now we're cooling back down to 202. Okay. So this is the flavor here you're going to see. We have a WOT event where we can see what lambda we were commanding. And afterwards we can see temps. For this situation, stock car, for all intents and purposes, we see after a WOT event that we got to 203 on the cylinder heads, 190 on the coolant, and this is at an ambient temperature of 70 degrees Fahrenheit, sucking 75 degree Fahrenheit air into the engine. So let's remember those numbers. 75 degree afternoon, we did a WOT pull, we got up to 190, 203. Now, let's close this file. And let's look for the fun file. If I go to my stage 1 tune and I look for mod when she was stage 1, we've got the power enrichment, along with a bunch of other goodies. Let's open this up. And if I go to a WOT event, this should be one of them. That's at 5,200. This one, though, okay, so we got up to 6,200, some sort of little dip, and then we hit it again, and that got up to 6,600. Pretty good. Let's also, just for fun, look at this. I guess we'll look at a bunch of these. All right, going back to this one. So, bottom of the mountain, we see we were 0.99 actual, and we were at 192 and 202 respectively for coolant and temp. As I start coming up here, right, this rich into 0.86. Ooh, that's higher than 0.83, isn't it? And if we keep coming here to the other top, wow, 0.85. 0.85 at peak power production here, right? That's pretty interesting. Somebody, right, has reset the PE lambda. Somebody. And if I follow this now, I'm going to see my coolant temp, my cylinder head temp. Oh, that was a little too far. Oh, maybe not. They went down dramatically. A little too quickly. Let me see here. What about this WOT pull? Once again, at the top here, we're talking 0.84. Okay. And then coolant's hitting 205. Here we go. Okay. So here was a WOT event. Coming in at the bottom of the mountain, we were at 199 and we were at 210. Right? And as after the pull, cylinder head temp, sorry I'm jumping around, watch it. 213, 14, 15, 17, 18, 19, 20, and we're cooling again. Okay, So, and the coolant temp, 208 to 220. Now remember on the other file, what was it, 190, 203? And on this file, go and rip shit, an isolated WOT event after a period of cooling, peak temps went, instead 190 went to 208, and 203 went to 220. And remember, the other file was on a 75-degree day. This, I believe, is a crisp autumn day, 50 degrees Fahrenheit, 54, right? I belabor the point because, again, if it's not real until you see it in the logs. The whiteboard theory, that's all fun and games. Talking on forums, shooting your mouth off on YouTube. I am not pointing at anyone in particular. I'm just saying you've got to be a critical thinker and find good information, and good information stands up to the acid test of bench testing. This is a good bench test. We saw with the software that if we go from 0.82 to 0.85 as our PE lambda, then our temperatures went from 203 roughly up to 220, right? Increased heat because of the leanness. But with that heat, I check and I see. Let's see here. Let's have a look. One of the biggest things I'm logging, knock retard. And you can see here, -1. Now, that is actually fairly typical. -1, we see a lot. It's not something you want to worry about too much. It's like a flicker. What you would want to look for, right, and what this means is that the ECU is retarding the timing by a degree, roughly. The ECU for the Coyote 4th Gen tends to do that during watt pulls just because it's a good idea. It's almost like it sets it up right on the edge, and if it needs more, it's right there ready to deliver it. KR in excess of 2. So if you're pulling more than 2 degrees timing for a sustained watt pull, you're too hot. Your power enrichment's too hot. And when I first started doing this file, I was careful to look and see. I'm not seeing anything quite like -2, right? And, you know, I painstakingly go through. You should do the same when you do what I'm about to show you. But this is what we want to see in the logs. And you must absolutely verify your thermal management. If you do power enrichment, and again, I'm going to show you how to cast Fireball here in a minute. If you go through power enrichment, your lambdas you should see change in the wideband, and you should see the corresponding increase in thermal load. And a little thermal load is okay because the engineers at the company said we don't want any thermal load whatsoever, right? So they leave it very conservative. We're increasing it a little bit. It's just like overclocking a CPU. The car is running right. I use good oil. I use 93 octane gas. There's no leaks in my plumbing, right? I've fully calibrated both my MAF and speed density airflow models and the corresponding gasoline mapping, right? Because I've been so disciplined, I have good, hard control. And with that control, I can slide from 0.82 to 0.85, leaning out my WOT Lambda. And that means I'm going to get more power out of the gasoline that I'm using. And I'm watching carefully to make sure that with that increased heat that I am watching carefully, I can manage it and I'm not seeing knock retard. Okay? So, the moment you've been waiting for. In your tune, to perform this procedure, you load up your engine tab, you go to Power Enrich, and you go to your good friend here, WOT Lambda, wide open throttle commanded lambda for power enrichment. And you get this magical little table. Okay. Now, this is what it looks like in stock form. Now, what's going on here? We have coolant temperatures across the top, and we have engine RPMs down the side here. And you will notice that, so first of all, you should know this, but if you don't, you never, ever, 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 ever go to WOT in a car that is not at operating temperature. The seals on your car, if they are cold, if you've just started it up and you hit WOT, they have not expanded enough because they're designed to increase slightly with the heat of the engine. Now, this is much less so in modern engines, but nonetheless, car lore, right? This is just, never into the wind, my son. This is basic advice for life. You never go watt until you know you're at operating temp, which we know that the oil temp should be, I believe, 230 degrees Fahrenheit, right? Your cylinder temps, you're going to above 190, right? Okay, so given all that. So that means we know that our coolant typically is above 180 Fahrenheit if we're at operating temperature. So we're going to absolutely live in this column, 160. This is the one that matters the most. The rest of these, but we're going to touch them anyway. And you will see here in this column, if it's watt, at the first stroke, we drop to 0.84. That is pretty wet for an idle condition. And then as soon as 3,000 RPM, we drop to 0.83. That is very wet, very rich. That thing's, that's not spraying a fine mist, right? That's hitting the kids with the hose, And all the way on through the power band, 5,000, 55, 57, 50, right? And as we get to approaching red line 6,000, we richen it up even more. Now we're really unloading with a fire hose into that cylinder and richening up to 0.82. That is very wet, okay? When we tune this, bing, it's pretty easy to do. You can highlight certain portions at once, and you can put your 0.85 and then hit equal sign. It'll touch them all up. This is the one that I have and how I've touched it up. I think that 0.85 is, from what I've read in various places, books, forums, seen on YouTube, seen on Facebook, right? Seen on Discords. I look at it all. I find in both the advice I get and with practice and looking at my logs, 0.85 for this area is pretty lean. It's adventurously lean, close to aggressively lean, but not insane lean, right? Like 0.88 would be insane lean. 0.85, it's pretty good. That's stout, right? But it's not crazy talk. It's not going all in with 10 jacks suited just because it feels right, if you are of the poker ilk. Then as we get close to 4,000, I richen up a little bit because this is following the pattern from the original file, so I'm kind of mimicking it. It's this one, 3,000, that I'm a little more aggressive. I keep that at my 0.85. And then up top, 0.85. So typically, and this is stuff that I've seen from the Miles of Speed world and other areas, when you get up top to the 6,000, 6,250, the torque band, when you look at it, the torque band sort of starts low, gets real high, and then up top it drops off a bit, right? How much power it's producing. And so you can get away with leaning it out a little bit up top, real high, right? Within 500 or red line. It's just a trick that I know. Believe me. And again, this is something, and because you'll see here, if you look at the Ford fellas, right, they really richen up that pocket. That is way too wet. And it goes counter to the performance kind of tuning that I've done in the past. And on this car, it has worked really well so far. I don't see knock retard. And that was when I was logging back in August, right? So I get aggressive up top here. And so then the rest of the file, right, for these areas, you just mimic what you have here for by and large. I just happen to be a little conservative here, and 4,000 I cool things off a bit, right? Otherwise we're mimicking, and then for these states as well, I leave them quite, reasonable, right? Conservative. So that's how you do it, right? Let me click off. There we go. You just come to this little table and you make these adjustments. And so what that means, again, is so down low during idle, the VCT schedule is going to control everything. It's going to use those phasers on the variable cams and all those different driving schedules and distance from optimal power. It's going to manage all that for you, right? And it knows that stoichiometric is 1.0, and it's constantly blending based on the situations between that 1.0, the partial states, and then what it would look like in optimal power. And that's the other thing. The relationship between moving from idle and low throttle states through partial throttle to power is the thing we need to talk about next, because a lot of people, they set this table. I've worked on systems where this is all you need to do. Master Speed 3s, for example, this is all you need to do. And it's very similar to an AFR grid. There's more to it, okay? That's just this area. If you are running flex fuel, okay, you are an adventurous chap, and you would need to come in here, and you would also need to work on your flex fuel tables. I am not running ethanol, right? I'm just the 10% in standard gas. If you're running E15, if you are full on running, if you are lucky enough to be one of those folks that's finding like 75, 80% ethanol in the wild, you're going to have to worry about this. Chances are, if you're that kind of fella, though, or gal, you know that you're going to need to touch that. So just explaining what that is. What's FFV? Flex fuel vehicle, okay? What we need to worry about over here is on our throttle what fuel enrichment pedal looks like. Okay, so before I open this, here's the thing. Swinging from one state to another causes problems in tunes. It makes things stutter. It makes things herky-jerky. It's the sign of it affects drivability, right? Good tuners produce cars that have drivability. Now, I'm not talking about, again, the world of drag racing, top fuel, right? We don't live in that world. That's not what we're doing here. We are making street drivable vehicles, right? So in the interest of that and things just working properly, if you go to the fuel enrichment pedal, originally what this table was saying was, throughout the power band, don't begin relying on optimal power fuel enrichment unless the pedal position is greater than 90% depressed, okay? So basically, don't engage in fuel enrichment power modeling unless it's like all the way to the floor, right? And that is very abrupt for someone who is a spirited driver. That might work for someone who very rarely goes to WOT. If you're the kind of person like me, gets into it a little more often, that can create a couple of issues. We want to tip in to power more elegantly, okay? And so we want to set some better values here, values that are more they anticipate going into a richer state for power production sooner rather than later. And so from like the 1,000 RPM state, if we had a throttle that was 73% or higher, right, we're going to start already using the PE flooding math, right, for flooding that cylinder with richness. At 1,050, at over 57%, halfway depressed, listen, with this guy driving the car, if we're over halfway depressed, it's coming. Right, so just start squirting fuel, right? And you can see above 6,500 in particular here, the way this table is set up. We changed that out. Okay, so that's one thing, fuel enrichment pedal. The other, though, is if you go into your airflow, and you remember our good friends, the variable camshaft, within optimum power, okay, remember we touched these to do the tuning for watt speed density. The other thing here is the enable pedal position. Okay, so the VCT schedule and the HDFX moving to the optimal power enrichment state, we originally it has it, you've got to be 70% depressed to get into that state and begin using it. Again, it's very herky-jerky. It's like all driving down here except what up here, right? As opposed to sort of we start here, and I'm trying to watch myself, and we go up smoothly, right? We don't want a binary step, right? We want a nice sort of smooth curve as we move into power often. So that's why we say here, better idea, if we're down low, real low, I'm not the kind of person who would suddenly go to WOT unless I really mean it, if I was down this low, right? But if I'm cruising around at 2,000, I'm often in fourth gear at 2,000 going through hill and dale, and the second the person in front of me makes a right or left turn, right, I'm into it, right, and off I go. So it's quite often in 2,000 I begin initiating partial throttle moving towards power. If I've gone above 3,000, I mean business, right? And that's where it's like pedal. You should only, instead of waiting all the way till you see 70, ECU rather, if you see 40, Mr. ECU, flood it, because it's coming, right? That's what I'm telling it here. It's a different pattern that allows me to tip in to power more easily, okay? And that is something that helps protect the engine. It keeps things cool from the get-go because, again, thermal management. By squirting fuel early and often, rather than waiting for very abrupt shifts, I help massage and manage my cylinder temperatures overall, because chances are if I've gone WOT once, probably going to do it again, right? So that is the nature of the